Let's use an example of writing a generic linked list to step through some of the concepts and some of the complications with generics in Java. The very first thing that many people might notice when looking at this generic linked list is it takes a generic type E, and its nodes or its cells take a different generic type V. This has to be the case in the way that this particular class is written because the nested class is static. Static things within a class cannot access the generic that was used for that particular class because E, the generic type, belongs to the specific instances that get created. In other words, when I say my linked list string, I am creating an instance of the my linked list class that has its generic defined to be string. But static spaces don't know things that belong to instances of a class. They only know things that belong to the whole class itself. When a generic type is compiled, the generics are sort of essentially washed away. And so the class itself will just be my linked list, and it will not know what its generic type is going to be. When we create instances of them, then the runtime will go in and fill in those particular types for wherever E existed. But it can only fill those types in for things that belong to that instance. So it will create, for example, an instance or multiple instances of cell that are given a specific type, that is the E. So if I create my linked list of string, it will then inside of that say, okay, my cells will have strings, which will then fill in for the V here and fill in that it's string, string, string in all of these places. But until I've created that instance, the static thing doesn't get any value for it. And so it cannot access the generic of the class itself. It has to have its own generic specified for it if I've declared this nested class to be static, which I have here. So this is an example of how those static namespaces and those non-static spaces can't quite overlap perfectly here. And they shouldn't. Static things belong to the class itself. And sometimes this is helpful, especially if I were to make this public so that people could create cells of a particular type and be able to test them out. You'll see my tests when you get to see them do this in a few different places to create a type that is of the nested class. So, however, this specifies a linked list, it will get a type, and then eventually that type will be fed to the cells themselves, but internally the cells have to use their own generic type that will get specified when those cells are created. There are 3 constructors shown here for the myLinkedList class, one which does essentially nothing, doesn't set up any variables or anything like that. It's a default constructor. There's another one where we could feed it an array of values. Notice that that array is of the type that our generic is of, so that I'm allowed to insert those values. So if you create a myLinked list of strings and you give it a string array, it's going to do just fine. It's going to call the default constructor, which does nothing at the moment, and then start to assign different items from that array into your linked list, assuming add first works properly. There's another that will take an iterable, which is a category of types. It's an interface in Java that it's something that can have an iterator created from it. It says that that iterable could have any type that extends E. So it could take an E itself, or it could take any type of class that extends E. So if, for instance, we had restricted that E was comparable types, because maybe later on I want to do less than and greater than kind of comparisons to them, then any comparable type would be allowed to be fed in here. And so we can take that iterable, it will create a new my linked list, and it will add each of those items from the iterable that was given to us, and it will then pull all of those into this linked list. This sort of allows us to kind of convert and treat those as E types here, where they could be any type that extends E. So we're allowed to add those items now into this linked list after having copied them over to the specified my linked list of type E. We've got some basic utility functions, getting the size, checking if it's empty, clearing it by setting the head to null and the size to 0. And then here is an interesting one where we get first. You'll notice its return type is of type E because it's going to return whatever type our generic data is. If the size of our linked list is 0, then we'll throw an exception. That's sort of reasonable. Otherwise, we'll return the heads element, and the element variable is the cell variable that is of the generic type. So we have E in the signature of get first, and we use that illegal state exception to specify that someone tried to do something that wouldn't work based on the state of the program. We've got some similar illegal state exceptions and even illegal argument exceptions for remove first and get. So this is removing the first item from our linked list, but if the size is 0, that's illegal state. We can't do that. We get the heads element otherwise. We set head equal to head next. Since this is a singly linked list, we're able to just step forward, and we decrease the size by 1 and then return the old heads element. Not too huge. We're allowed to create a variable of the generic type. We're allowed to return that variable of the generic type, and our return type is of the generic type. Similarly, get will just step us out to whatever index was requested, and we'll return the element from that one. We don't have to do any special saving of the element, but we did have to create a cell variable. We had to specify that it was a cell of E objects and start it at the head and step it, and then we're returning its element. So this is holding the cell temporarily that we're stepping to and then getting the element from it. We have to instantiate that cell as cell E because, again, cells are static. They don't know our generic type until we tell it to them. And so we have to establish that this is a cell of E's. Our remove does similar things to what our get did, checking that the argument was okay, checking that the state of our list is okay to remove things, and if the thing is 0, then we just call to remove first. Why waste the effort? We'll just go ahead and call the established method that does that. Otherwise, its structure is pretty similar to get. It will get a cell of type E and step until it gets to the right index, and then it holds on to the value, the E type, from that element because it's going to set C's next to be the one after its current next and skip past the element that we are returning values from, removing it from the list essentially there. And add first will create a new cell and set that cell's next to be the head. If the head was null, this is okay because that cell's next will be null, meaning that we've reached the end of the list, and setting the head to be equal to C, this new cell that we created, and increasing the size. It has a parameter type of type E because that's the data it's going to be adding to the cell that gets created here. Add is similar, except it has to get to that n location. So if n was 0, it will just call add first, but otherwise it does this starting at the head and stepping to the next, until it reaches the index we're supposed to be adding at. It creates a new cell just like add first did, but it's going to be setting the next of that new cell to c.next, and then making that new cell be c's next and adding to the size. Here we get a little tricky. So we want to fill a linked list and create a new linked list. So this is a static method, not one of the ones that belongs to a particular instance of linked list, but this is going to generate a linked list for us. So if someone wanted to create a linked list that was all zeros, or was all the same person's name, or whatever they wanted to do, they can do that. They give a value and they give how much or how big they want that linked list to be. But because it doesn't belong to a particular instance of linked list, we give it its own generic type with this method. We can create generic methods in any class we want. In this case, we're creating a linked list of whatever type of data the person gives us. So they can call mylinkedlist.fill and give it some value and a count of how many items should go into that linked list. And this is just going to loop and add first over and over again to a linked list of whatever type of data they gave us. They don't have to specify that they're going to get out of this a linked list of strings or whatever thing. Java will look at the type of data that is created here or is given here, and it will create a linked list with that type of data. Now, their variable types may need to match, so they may have to specify that it's a mylinked list of strings, L equals mylinkedlist.fill, and then they give it the string or whatever the value is that they want it to fill with. So those types will need to perhaps match. But Java will infer for calling this function or calling this method whatever the type of the linked list is supposed to be based on the type of the data that was given to it as a parameter here. That t, because this is a static method, we give that t and it's independent from the class parameter e. In fact, we would not be able to refer to e inside of this method because, again, those e's get defined for an instance of my linked list. They don't get defined for the static space that belongs to the whole class. We can create an object array and return everything from our linked list class as an array of objects. Because everything in Java inherits from object, it's safe to do this. It doesn't matter if you created a linked list of strings or of cats or of scanners or whatever, you can return those as an array of objects because all of those and all Java objects inherit from object. So you'll often see these two object array type of methods for collections. You create an array of objects with the same size as your linked list. You then do that looping from the head to the next and next and next. And as you do each step in the loop, you save your element to index I. Pretty easy. And this is a pretty standard way to create an array. What we cannot easily do is create a method that returns an array of the actual type our linked list stores. At compile time, Java needs to know the actual type of all arrays that are being instantiated. You're actually allowed to set up the variable of the array, but you cannot say equals new e array of size 5 or things like that. Java needs to know what the type is whenever new is being done. This also means that you can't call the constructor of e and construct a new e object. You can again create a variable, e thing equals something from your linked list. That's allowed. You cannot say e thing equals new e. You wouldn't know what parameters to give to the constructor, and Java can't confirm that that class even has a constructor if you used an interface or some other type as what's being stored in your generic there. So you cannot create arrays, newly sized arrays of generic types in Java. If you learn what their type is, which we'll see some ways to figure out the types of things in Java, the types that things actually have in Java, you may actually be able to do this. It's a little funny and you'll have to take some parameters perhaps. But for our purposes right now, until later when we look at reflection, then for now, we're going to say you cannot create this generic array returning method here. Once we look at reflection, we're able to figure out the types that we're using at runtime, then we might be able to. But for now, Java's going to say, if you say eArray x equals new eArray of size 5, you will get a compiler error because you cannot instantiate a new E, and you cannot instantiate a new array of type E. We have a sort method written here that will compile and not give us any warnings, but is actually useless. So it tries to call the Java util arrays sort on our data, but our data is not guaranteed to have a meaningful way to be sorted. And in fact, we even just said a moment ago that turning our data to an array of its generic type is not going to be possible for us for the moment. So this would compile, but it's not actually going to do its job. What we can do is we can create our object array, and then we can call for the array to be sorted using the object comparator. A comparator is a tool that will allow us to tell whether one item should go before or after another item. You can look up that type in the Java APIs to see how a comparator works exactly. But there is this nice arrays.sort function that's built into Java, and we could give it an array and a comparator, and it will use that comparison tool to sort the array. Here we're clearing out our linked list after that, and then we're adding first for each of these. However, we will get 2 warnings on this because we are casting our data to be T's after pulling it out of an object array. It's a warning that we probably can get by ignoring because the data that we put into the object array we know was from a linked list of T's, and we're turning it back to T's. Nothing should have stopped it from being the same kind of data that it was in the sort of interim period there. So this should be okay. It doesn't look nice to have those warnings, but we are able to turn it to objects and then have it sorted and then turn it back to T's to add to our linked list again. So it is a way that we could sort our data here. It's worth noting that you're able to use these sort of boundings on generics to say that something can be a supertype of C, a parent class or a parent's parent class or a parent interface or a parent's parent interface or so on. So we're saying that anything that can compare T's or any class that's above T in its hierarchy we'll accept as a comparator here. And that way, if T was a subclass of something that was nicely comparable, we can sort of look up to its parent class and use whatever comparison tool exists for that parent class or its parent's parent or so on. You'll notice again that we had to cast to a comparator for objects. And so we're still using whatever comparator was fed in. We know that it can compare T's or a parent class of T's, but we're casting it to a comparator of objects. Java will go ahead and use it because we've made it okay for Java to see it as working on object arrays then. These casts are not clean, but they'll work okay. Similar for our clone here. We want to clone our linked list and be able to make a copy of it, well, it's going to return an object, which we'll have to cast back to being a linked list outside of this. It's a little messy there. But we can try to create a new linked list of e's and then call a superclass clone. And then we go through and we step and we grab. So this just does an object clone, creates the sort of base object for it when we call it to the super.clone there. And then if the head is null, we'll just go ahead and return that empty linked list that we just created there. And if it is not null, then we'll set the new list's head to be a new cell of our head's element. And then we will start to step through and not just create the cells, but also set their nexts correctly as well, so that the linked list is properly linked and contains all of the data that was in our original linked list, this linked list. You'll notice that, for instance, where we say head, we're saying this dot head essentially here, and that where we have B is L dot head. There might be more meaningful names we could have used for this here, like cur this, cur L, or something like that, so that we know we're dealing with one from our list, this dot head and so on, and one from L, the clone that we're making. So this will copy the data, it will set the nexts, and it will step forward to the nexts to be able to continue setting next, copying data, setting next, copying data. And we will still get some unchecked cast warnings from this one by having to convert the object that comes out of super.clone into a linked list of e's. It's not perfectly clean, but we know it's safe because we know that we are dealing with the same type at all points throughout there. So to summarize some of this, generics allow us to create types that can then be given parameters of what they're going to store, like a linked list of integers or a linked list of strings. We write the functionality once, rather than having to write a string list and an integer list and a whatever else list. We write the functionality once by using the parameterized types of a generic. But then at the time that we actually specify the type, Java is able to sort of fill in that type for the object instance that's being created. It's worth noting that list integer is not a subtype of list number. Even though integer arrays are subtypes of number arrays, we're allowed to do that. We're allowed to store integer arrays in a variable that was declared for number arrays. That's okay in Java. We may get some array store exceptions if we store the wrong subtype of number inside of there, but we're allowed to treat those as being related types. But a list of integers is not treated as a subtype of a list of numbers. If we do a list of integers, it can be a subtype of a list where we sort of bound the type. So when we specify the type, Java will be strict. It will say, no, you created a list of numbers. That is not related to a list of integers. So what we do instead is we bound the type with this something extends something or something super something. So we can do that in a sort of anonymous throwaway way, like question mark extends t. And that tells us it's going to be some kind of subtype of t. Or we can name it. We can say s extends t, and then that gives us a specific type. One of the common ways you'll see from this is something like s extends comparable. Again, if I want to be able to call compare to on the data that is fed into my generic type here, then I could say s extends comparable, and I'll know that all of my s values that are given to me, the compiler will ensure they all have a compare to method, they all inherit from comparable. We could do the same for things that we want to be sure are drawable. If we were doing a graphical program, then we could ensure that all the things stored in our data type were drawable so that we could draw them to the screen. We can bound in either direction by saying that we know that what we're given should be a subtype of T, or we can bound in the upward direction saying that whatever we're given is a parent type or a supertype of T. So these boundings can be useful. Either we don't name them or we do. It's up to you based on whether you need to refer to that S type later, or you can just leave it as a question mark. But that does allow us some more flexibility. If we say list of integer, it must be a list of integers. And if we say list of number, it must be a list of numbers. But we can use the bounding to kind of loosen it up, but guarantee that there's still some relationship there. And so possibly be able to guarantee that there are shared behaviors, like I might want to make sure for a sum method, S-U-M, sum, that I'm extending number. I'm using things that extend number because I know I can add them. I can get a sum of them. And so this kind of bounding allows me to be loose. It could be integers, it could be doubles. It doesn't matter too much as long as I know that they have number functionality. Again, we cannot create arrays of generic parameter types. We cannot create new arrays of those types. We can't say equals new array of E or anything like that, because at compile time, Java needs to know the type of arrays when new is being done for them, when they're being told to allocate a new array. The compiler will want to know that type at that time. Static methods and classes cannot access the generic parameter. They need to have their own generic parameters. We've seen examples of that for both a method and a class here. And again, this hopefully makes some sense because static means that it belongs to the class, not to instances. And we only define the generic type for instances. We have an instance of list which contains integers. We have an instance of list which contains strings. But the static space doesn't connect with those instances. So it needs to have its own generic type specified. Now, in terms of classes, all stacks have the same class. All linked lists have the same class, and this makes sense. They all come from the same something.java file. They do not have the same type in memory. So I'm very careful to use the word type when I mean type, and class when I mean class. That when I instantiate linked list, my linked list, all of those come from the same class. And so when we move on to talking about reflection and looking at what classes are behind the scenes from an object, they will have the same class, and therefore they will share all static methods and attributes. And when we do that reflection, they will have the same class object that we'll use to refer to and learn about them. So for instance, if I created a counter that was a static variable of how many stacks have ever been made, then it doesn't matter whether they were stacks of strings or stacks of numbers or whatever, that static counter will belong to all stacks of all types. And so again, hopefully this makes sense. If I were counting all the stacks that have ever been made, I didn't say only stacks of numbers. I said all stacks. If I want some maximum limit on how big a stack can become, a max stack size, I could make that a static variable, and that would be the limit on stacks of numbers and on stacks of strings and on stacks of pancakes if I had an object or a class to represent pancakes. It does not matter. Those static things will be shared among all of the versions of stack that ever get instantiated with a specific type for that generic. So there's a little bit of juggling here to do between the concept of the class, which has a generic defined for it, but not a specific type, and the instances, which have filled in the dots of what that generic type will be, and they have their own specific type at that point. And you'll get some more chances to play with these, and we'll look at some more examples as we go through of how these generics can really be used to stitch together some shared class behavior, but allow broader behavior for the specific instances and the types of data that they can store.